वाला part throw us a length. I say this next part that's slightly lengthy, which is that colors. We haven't talked about why they are colored. But just wanted to show you, they're asking about the color of the following solutions. This is a blue solution. Okay, this one is a blue solution. This other one is a greenish yellow or a yellow solution. I've got this. So here's case stability. You can see case stability, which is that when you have an aqueous complex, there's an aqueous ion in solution, and it's forming this complex. So if you've got a big value, that means I told you that what is case stability? It's the concentration of the products divided by the reactants. It's the equilibrium constant of a ligand exchange reaction. Yahan pe, what is the complex? It's silver ions in water. It's silver surrounded by water molecules, and those water molecules are getting knocked out and they're getting replaced by NH3. Okay, so there's a ligand exchange happening, and it's got a very big case stability value. That means more products are getting formed. Okay, this means that the product concentration is like really large and the reactant concentration is like really small. So there's a very high chance of the products getting formed. So that is what case stability is. So one second. I said then the same thing, copper sulfate. Remember, you're going to get the question on cobalt as well. In past papers, you mostly are going to see copper, but cobalt is now added in your course. So I did give you the colors. I told you that everything is exactly the same. Okay, copper with ammonia, that's going to be copper with either a few drops of ammonia. That would result in the formation of copper hydroxide. That's a pale blue precipitate. Copper with excess ammonia, it's going to get surrounded by NH3s, 6 of them, or maybe a few NH3s and a few water molecules. Copper with NaOH, that would also result in the formation of copper hydroxide, which is a pale blue precipitate. Copper with Cl, that's CuCl4, 2-. So जो कुछ हमने यहाँ पे पढ़ा ना, exactly the same thing would kind of be over here. Okay, if you add a few drops of ammonia, what happens is that the ammonia ends up forming water molecules, or so the ammonia ends up forming not water molecules, it ends up reacting as a base with water, forms OH ions, and what those OH ions are going to do is that they're going to form copper hydroxide. When you add excess ammonia, then the ammonia comes in and starts knocking out the water molecules and takes its place, and it forms a deep blue solution. So exactly where, there's nothing different. All that's written in the notes, everything is exactly the same. Here's another case stability. It's Fe with water, and you're replacing it with Cl ions. He's asking you to write the expression. So I told you that when you write the expression, you don't write water, because in aqueous solution, water is taken as a constant. So it's going to be FeCl4 minus its concentration, and the whole thing gets divided by Fe. This complex plus 3, sorry. Its concentration and Cl minus 1 concentration, that's going to be power 4. And the numerical value of case stability is 0.08. So that's kind of low. It's a small value. So if the value is small, then there's going to be very little chance of this actually forming. He's asking calculate the concentration of FeH2O6 in a solution in which the concentration of Cl is 2 mole and the concentration. So everything is given. Case stability is given. FeCl4 minus 1, its concentration is also given. Cl concentration is also given. That's 2 mole per dm cube. If everything is given, you can find out the concentration of FeH2O6 as well. So you're going to get questions, very simple questions like this in for case stability. So Baki, this one. Now we're going to talk about something that's slightly more difficult. It's again We're going to learn something and they're going to ask you exactly the same thing. What's the origin of color? Why are they colored? Why are transition metals colored? So that's the next thing. We've studied all these complexes. And the next thing that we're going to study is, so आवाज आ रही है Sana, can you hear me? Sidra, Naseeb?
Yes, sir.
So the next thing we're going to study is why are they colored? So why are transition metal complexes colored? Complexes colored. Now, before doing that, we're going to learn that every transition metal has a D subshell. We learned that they form stable lines that have incomplete D subshells. Now that is essential for colors. So every transition metal has a stable ion that has incomplete D subshell. If it doesn't, then it won't be colored. So the number one reason why they're colored is because it's because of this. So that would mean it's going to have a colored complex. If not, then it's not going to have a colored complex. So for example, so if you don't have incomplete D subshell, then you're not going to be colored. So if Hanji.
Sir, incomplete D subshell तो सिर्फ ये represent कर रहा है कि electronic configuration like क्या है और मतलब वो electron gain करेगा.
मैं बता दूं D या तो 5 हो या 6 हो या 7 हो. You can't have D10. Well, I'll explain the reason, but the first rule is for colors to appear, you need to have an incomplete. If no incomplete D subshell, then not colored. Not colored means white. Okay, for example, copper plus one complexes are white. Or if they form a solution, they're going to be colorless. ठीक है, मतलब example, copper 1 chloride, let's say. So copper 1 chloride, if you look at copper 1 chloride, this is copper, ये वाला है. ठीक है, this is copper 1 chloride and that's white in color. ठीक है, वो कुछ salts में ना colors appear होते हैं because not all of it is copper 1. उसमें ना बीच में there would be some copper 2 as well or something, but pure copper 1 chloride is going to be white in color. Copper 2 chloride will be actually colored. So copper 1 is white. ठीक है, and the thing that copper 1 is that copper 1 has a full D subshell. That when you have a copper 1 salt, let's go again, plus 1. Copper 1 means the electronic configuration is argon. That's 18 electrons. Argon that's then 4s2. Sorry, it's actually 3d10 and 4s0. I mean, it was 4s1, but now it's 0. So that's the electronic configuration of copper plus 1. So the D is full. So anyway, so what you need is you need to have incomplete D subshell. That's extremely important. Okay, so you got to have incomplete D subshell. Now, what's so important about incomplete D subshell that it ends up resulting in colored complexes? So first thing, what's a D subshell? So the D subshell looks like this. Let me just paste an image. It's you've got 5 D orbitals. ये वाली drawing अच्छी है. But let's take this one. So that's like a typical D subshell. It's like it's got 4 lobes. You should remember they'll ask you to draw this. So that's your D subshell. And your D subshell has 5 different orbitals. The important thing is, so there are 5 different orbitals, and they're degenerate orbitals. You've got dxy, you've got dxz, you've got dyz, and you've got dx square minus y square, and you've got dz square. So you've got 5 of them. Now, since you have 5 orbitals, a maximum of 10 electrons can be accommodated in those 5 orbitals. The thing is that if you look closely at dxy, it's the electron density lies between the, sorry, this is the dyz. The electron density lies between the y over here and the z axis over here. The electron density is right in the middle of the y and z axis. If you look at the dxz, the electron density lies between the x and the z axis. This is the z axis, this is the x axis, so the electron density is right in the middle. dxy, electron density lies between the x and y axis. Then you've got the dx square minus y square. That's just a name. It means the electron density lies exactly on the x and y axis. And then finally, you have the 5th one, which is the dz square, which looks different from all the other ones. But these are your typical. Yes, Asif, they can actually ask you to draw any one of them. They can actually, I mean, usually what they do is I'll show you the example. They'll ask you to identify them. Just a second. And for example, over here, so you've got a question over here, and they might, I mean, the question is something else, but maybe they might ask you to identify them, right? So you should be able to identify this. Like, this is electron density lying right on the x and y axis. So that's your dx square minus y square. This over here is your dz square. This one, the electron density lies, if you can see this, it's lying between the x and y axis. So that's your dxy. Over here, the electron density is lying between the z and the x axis. This is the x-axis, this is the z-axis, electron density is right in the middle, so that's the dxc. And this one is the electron density lying between the z and the y-axis. So this is the y-axis, this is the z-axis, so that's your dyz.
So,
हाँ जी.
सर हमें पता कैसे चलेगा कि कौन से ऑर्बिट के इलेक्ट्रॉन डेंसिटी कहाँ पे ज्यादा होगी?
नहीं, ये पांचों है ना, पांचों ऑर्बिटल्स है ना. पहले तो अभी हमसे वो करेगा आइडेंटिफाई करना. Can you identify it? So if it's between the x and y axis, that's your dxy. If it's z axis, that's your dz square. If it's on the x and y axis, that's your dx square minus y square. If it's between the z and the x axis, ये z और x axis के बीच में, then that's your dxz. And if it's between the y and z axis, that's your dyz. Is that clear?
Yes, sir.
ठीक है, तो अभी तो फिलहाल बस आइडेंटिफाई करना है कि let's say they ask you to identify them, right? Now remember, you have a total of 5 orbitals, and all of them are degenerate orbitals. That means electron density has, I mean, all 5 are exactly identical. The orientation is the only thing that's different. Apart from the last one looks different as well. अच्छा, लेकिन आगे moving forward, one important thing that you should note over here is that these 3 orbitals over here, these ones, if you look carefully, their electron density lies between the axes. It's always lying between the axes for dxy, dxc, dyz. और ये जो दो है ना, जो bottom ones, ठीक है, these ones, their electron density is lying on the axis. So that one, the electron density lies exactly on the axis. dz squared, the electron density electron is exactly on the z-axis. Dx squared minus y squared, the negative charge is distributed on the x and y axis exactly. Okay, this will come in handy. Okay, we'll talk about it later. Now here's what happens when a complex is formed. Imagine there's a nucleus and electrons are getting added to that, right? So electron density is occupied between the z and y axis, right? So that space is occupied. There's an electron present between the z and x axis. There's negative charge between the z and x axis. There's negative charge that's present between the x and y axis. The only spaces left is the x and y axis. So there's an electron present on the x and y axis. तो पीछे सिर्फ एक ही जगह खाली रह गया. That's the fifth space available that's just on the z-axis, because all the other spaces are completely occupied with electrons. Okay, is that clear? See, clear? Yes, okay, three-dimensional space where there's no other space left where you could. Orbitals को ना imagine क्या करो, they're just spaces around the nucleus where you put electrons. Okay, where the electron occupies a certain space around the nucleus. तो दो electrons इधर आ गए, दो electrons इधर आ गए, दो इधर आ गए, दो इधर आ गए, पीछे बस एक z axis ही बचा है, वहां पे फिर वो बाकी जो दो electron है, they will occupy that space. Now, anyways, the next thing is, what do we do with this? So let's return back to our complex, and let's talk about any complex like an Fe complex, right? So you've got copper ka hi kar lete hain. Copper, sare questions copper pe hi honge. Let's do copper. Now the copper 2 plus is the one that's colored, right? So copper 2 plus has the original electronic configuration is argon. 18 electrons, then it's 3d10 and 4s1. Now copper was a special case where a completely filled configuration, d subshell is more stable. Anyway, so when a copper plus 2 ion is formed, electrons are lost from the outer shell, which is the 4s, and one electron is also lost from the 3d. So it's got an incomplete d subshell. So that means it's going to form colored complexes. Now here's your copper ion. So you've got your copper ion. Let's imagine that's your copper plus 2 ion, and there's a copper sitting right in the middle. Copper and its nucleus, right? Now remember, electrons are lost from the outer shell. The fourth shell of copper is gone. A few electrons from the 3d are gone as well, but the fourth shell is gone. Now imagine all the d subshell. That's all these d subshells are present. They're present inside the atom, inside the ion, right? There's a copper 2 plus ion and all the orbitals. Agar main puri electronic configuration likhu na, if I just write the whole of it, the whole of it is going to be what? It's going to be 1s2. Then you have 2s2, then you have 2p6. Then you have 3s2 and 3p6. And then you have the 3d9 and the 4s2. Now the outer shell is gone. So the outermost shell, electron is lost. And one electron from the 3d is also gone. So all these subshells are inside the ion. There's a boundary, outer boundary, and all of them are inside the atom. And now copper has 6 sides when it forms a complex, an octahedral complex. It has an x, y, and z axis. So let me draw that. So this is my x axis. Okay, so then I have my y axis. I say, anyways, this is what copper would look like. And all these orbitals, the d subshells, and not only the d, the p, the s, the smaller p, the smaller shell p, there's the two more s's. All these orbitals are inside the copper ion. Okay, so you've got orbitals which are lying between the axes. So I'm only focusing on the d subshell. Okay, I'm ignoring all the other subshells. I'm only interested in the d subshell. ठीक है, बाकी सारे मैं ignore कर रहा हूँ. ठीक है, not focusing on them. So anyways, I've got my d subshell. The d subshell were of two types. There was electron density that was lying between the nucleus, and let me. So there was electron density that's existing, and there's electron density that's existing between the axes, right? So you've got all sorts. So I've got all sorts of d subshells. So ये एक d subshell हो गया. As I've got another d subshell, I've got another d subshell, and I've got another d subshell. Now think of this in 3 dimensions. I'm basically trying to draw the first 3. I mean, you've got plenty of lobes, although I haven't drawn all of them because it would be very hard for me to draw this. But imagine this, that there's an X, Y, and Z axis, and there's electron density that lies between the axis, right? So 3 of my D subshells would be existing between the axis. Then I'll have D subshells, D orbitals, which would be lying on the axis. So there's going to be a certain d orbital that would be existing on the axis. There's going to be an electron that will exist on the axis. Okay, so I've got all these blue ones where the electron density exists on the axis. So imagine karo, I'm actually trying to draw all of them together. Okay, so I've got this copper ion and it's surrounded by electrons in the d subshell. Some of the d subshell electrons are between the axes and some of the d subshell electrons are lying on the axis. Okay, so the idea clear hai this is clear hai this is what the d subshell would look like for a copper ion, copper +2. Is that clear?
Sir, what is the shaded region? Is it Z?
नहीं, वो ये XYZ axis है ना, इसको मैं 3 dimensional मैंने draw किया हुआ है कि this is your x axis. वो इस तरह शो करना चाहूँ कि वो पेज से बाहर आ रहा है, मतलब पीछे से आ रहा है और बाहर की तरफ जा रहा है. ये शेडेड ना?
Yes, sir, clear.
ये y axis है और this one is my z axis. हाँ जी.
सर वैसे हमें पता कैसे चले कि ये कौन सी शेप को लाइक आउट ऑफ ऑल द 5 शेप्स कौन सा रिप्रेजेंट करता है?
नहीं, ये मैं सारों को इकट्ठा ड्रॉ कर रहा हूँ ना.
ओ तो 5 को डायग्राम जितने 5
के 5 मैंने इकट्ठे ड्रॉ कर दिए. मैं तो रफ स्केच किया है, मतलब ये एग्जैक्ट तो नहीं है कि वो पांचों को इकट्ठा ड्रॉ करना तो मुश्किल होगा ना. वैसे तो विजुलाइज कर सकते हो ना कि there's electrons between the x and z axis, between the x and z axis, between the y and z axis, between the x and y axis, on the x and y axis, on the z axis. ठीक है, तो ये आइडिया क्लियर है कि मैंने उसके अंदर एक्सिस ड्रॉ किए हैं and I've drawn all the d orbitals. Is that clear?
यस
रफ स्केच है, ठीक है, असल है अभी नहीं. अच्छा, अब होगा क्या? What happens when a complex gets formed? What happens is, so imagine these are your x, y, and z axes. Now the d subshell, how would dz square z axis पे होगा ना? Let's say this blue one is on the z axis. वो जो एक लोब नहीं रह गया था, that's on the z axis. So imagine this is the z axis and let's say this blue one is on the z axis. Is that clear? So Alicia, ये rough sketch है, मतलब exact 100% वो sketch नहीं है. अच्छा, तो I'm just trying to explain that what's going to happen is that this copper 2+ ion is going to attract, when you mix it in water, it's going to attract ligands. So there's going to be a water molecule that's going to be attracted to it. The water molecules, lone pairs are going to be attracted to it. Why? Because it's copper 2 plus, right? So the lone pairs are negatively charged. So water molecules are going to get attracted in an octahedral complex to the copper 2 plus ions, and they're going to start surrounding it from all sides. Now, when that happens, ठीक है, तो यहां से भी water आ गया, और लोन पे एक यहां से आ गया. अच्छा, now और एक यहां से आ गया. अच्छा, now what will happen is when this happens, अब पहले जो आपका D subshell था ना, that was degenerate. That used to be degenerate. Degenerate means that they're identical. They have the same energy levels. Well, I'm going to write this. I mean, the D subshell initially is degenerate. All they have exactly the same energy level. Which means they're all identical. The orientation is the only thing that's different. Otherwise, whether the electron is over here or the electron is over here or over here, it's exactly the same thing. Achha, but now what will happen is, because of this, now what will happen is, when the ligands approach, what happens is that it kind of becomes harder to keep electrons in these blue orbitals. ये जो blue वाले ना जिनको मैं shade कर रहा हूँ, it's going to become slightly harder to keep electrons over there. क्या reason होगी वैसे? क्या नजर आ रहा है? Why is it becoming harder to keep electrons in these blue ones?
Sir, higher energy.
नहीं, लेकिन क्यों? मतलब why is it harder to keep electrons here? जब water का molecule
Electron repulsion.
Electron repulsion, ठीक है? You've got electron repulsion happening now. Because when this ligand, पहले तो the water molecule was away. When it approaches and gets attracted to the copper 2 plus, the water का जो lone pair है, that's like right next to it, right? So there's going to be a lot of repulsion because of that water molecule. ठीक है? So the lone pair over here is going to repel the electrons which are over here. So it's going to become slightly easier to actually keep electrons in this other one, जो बीच में जगह नहीं है. So it kind of becomes easier to keep electrons in this middle area over here. ठीक है? तो वो जो axis के बीच वाला जो area ना, that becomes slightly more attractive to keep electrons, or it becomes slightly easier to keep electrons over there. So because of electron repulsion. तो ये बात clear है सारों को? Is this clear to everyone?
Yes, sir.
तो ठीक है, सारा clear है? Alicia, Anna?
Yes, sir.
Sir,
हाँ.
sir ये red region में कम repulsion होगी?
हाँ, कम, क्योंकि दूर है ना. मतलब water का molecule आ रहा है, water का molecule axis पे आ रहा है ना, octahedral complex में. All the water molecules will be approaching. जब 6 bonds होते हैं, what is the shape? It's octahedral, that all the bonds are formed on the axis, right? The water molecule तो सीधा उस blue वाले के सामने आ रहा है ना. अगर वो attract होता है, तो it's going to be over here. So it's like really close to the blue one. The blue one में electron रखना, it's difficult. Easier to keep electrons in the middle one, right? So now here's the reason for the colors appearing. So what has happened now is, कि उसी को copy करें. What has happened now is, your D subshell is no longer degenerate, which means it's no longer exactly the same anymore. What has happened is, ये क्या copy हो गया? एक second. So what has happened is, your D subshell has split into 2 separate energy levels. There's a place where it's easier to keep electrons, and then there's a place where it's actually harder to keep electrons. So जो middle वाले areas है ना, it's easier to keep electrons in the middle area. So in the pink ones over there. So it's easier to keep electrons over there. वो कौन से वाले थे? Your dxy, your dxz. And your dyz. And it's going to become a lot harder to keep electrons on the axis. So it's going to become harder to keep electrons on the x and y axis and on the z axis. And that creates an energy gap. Okay, your D subshell has actually split into two different energy levels, and there's this very specific and unique energy gap that exists between the two sets of orbitals. Okay, so your electron might be like, if I draw an electron, now this electron over here, okay, this electron over here might be I mean, it would prefer to occupy the D subshell. That's between the axis, right? But the same electron would need to gain energy to go into the blue orbital, because over there it's going to face a lot of repulsion. It would be a lot harder for it to actually stay in that area. So the electron over here will try to prefer to stay. जो D subshell के electrons होंगे, they're going to try and prefer staying in the middle part. And it would be much harder for it to occupy areas which are in the blue areas, right? So there's this energy gap that exists. And the reason you have colors is, okay, there's nothing unique about colors actually in the first place. What is unique is the D subshell was incompletely filled. So you had two electrons. Copper ke case mein you had 9 electrons. There was 2 electrons over here and there was 1 electron over here. Now electrons can actually jump because the D subshell has some space available. So an electron from the lower energy, for example, there might be 1 electron from here, could actually move and it might jump to a higher energy subshell. So electrons can sort of switch around as long as there's space available. Okay, that's why the D subshell has to be incompletely filled, because if it is incompletely filled, the electrons can't move around in between the D subshell. You need to have a space available. So that's why an electron could jump and move to a higher energy. And when it does that, that electron will specifically absorb a specific amount of energy, delta E. And the good thing about this delta E is that it matches frequencies which belong to the visible spectrum. So this energy gap matches frequencies that belong to the or are from the visible spectrum. Hanji.
सर ये इसको तो रेफर नहीं करता वो ब्रैकेट सीरीज पी फंड सीरीज वो उससे तो नहीं है
नहीं अब मैं वही उसको भी डिस्कस कर लेते हैं, लेकिन ये उससे लिंक नहीं है. असल में दिस एनर्जी गैप इज वेरी यूनिक, क्योंकि remember electrons in any atom, they can move around. ठीक है, मतलब अगर if I draw a sodium atom, like sodium is 2, 8 and 1, right? So you got 2 and 8 and you got 1 electron. ठीक है, एक सेकंड को सेट कर लें. अच्छा, so let's imagine that this is my sodium atom, right? Now sodium has 2 electrons in the first shell and 8 electrons in the second shell, and it's got 1 electron in the last shell. Now remember, all atoms, their electrons go into excited state. Okay, हवा से या sun से ना, there's frequencies, all sorts of electromagnetic frequencies, from X-rays to gamma rays to radio waves to, I mean, there are all sorts of frequencies around you. So there's an electron, and let's say this electron over here, it gets energetic. So what it will do is it's going to absorb this frequency and it will move to a higher energy subshell, right? Or shell. Maybe this electron gains energy from the spectrum and it absorbs energy and moves to a higher energy. So electrons are in an atom are constantly going into excited state, and they're also constantly coming back from an excited state. They might lose energy and they might fall back into a low energy state. लेकिन होता ये कि all those electrons are absorbing energies from frequencies that don't belong to the visible spectrum. तो अगर आपके इर्द गिर्द ना let's say एक टेबल है आपका ना, और वो टेबल जो है ना लैंप जो भी बल्ब जला हुआ है उसकी इंफ्रारेड फ्रीक्वेंसीज को एब्जॉर्ब कर रहा है, तो मुझे तो आपको क्या नजर आएगा? आपको कुछ भी नहीं नजर आएगा. You won't be able to see any difference because if it absorbs infrared and the infrared frequency gets absorbed and it goes missing, you were not able to see the infrared in the first place. So when it's missing, you won't even notice it missing, right? So ये clear है कि almost all atoms and all electrons, they're constantly absorbing frequencies and they're constantly going into excited state. The reason they're not special to us is, जैसे आपका phone क्या, which frequency is it absorbing? It's absorbing radio waves, right? So do you notice anything happening around you? You don't notice anything. Why? Because you didn't even notice radio waves in the first place. So when they're missing, you won't be able to tell whether they're missing or not. ठीक है? So is this clear? लेकिन अगर एक torch है which emits blue light, you'll if it's on, it's emitting blue light, you'll be able to see that frequency because your eye can only see very limited frequencies. So is that clear? Idea ये clear है कि almost all atoms, the electrons are kind of jumping around, right? They're absorbing energies and they're absorbing frequencies, but most of the time those frequencies, they don't have anything to do with you. ये बात clear? हाँ जी.
सर वैसे अगर इलेक्ट्रॉन अगर एक्साइट हो जाते हैं तो वो क्या मतलब अनस्टेबल नहीं होंगे वैसे?
बेशक आंसर जो मर्जी करें, वो इलेक्ट्रॉन एनर्जी गेन करके बाहर भी निकल सकता है, चला गया दूर, वो जो मर्जी करे, मैं उससे कंसर्न नहीं हूँ. वो एक्साइटेड स्टेट पे जाके जो मर्जी करे, आई एम नॉट कंसर्न विद दैट एट द मोमेंट. ठीक है, आई एम जस्ट सेइंग कि एन इलेक्ट्रॉन कैन absorb energy, right?
Yes sir.
And all atoms, all objects around you, they're constantly not only absorbing energy, they're constantly emitting energy as well. ठीक है, तो अगर आप लाइट को ऑफ करते हो ना, when you turn off a light, so it's still emitting frequencies. The only thing is it's emitting frequencies that you can't see. So you just feel that it's turned off, but it's not actually off. It's emitting a lot of frequency because it's hot, so it's emitting a lot of infrared frequencies. So the thing is, okay, there's nothing special. The special thing about ये बंद करो. अच्छा, मैं वो कह रहा हूँ स्पेशल क्या है. The special thing about transition metals is that this very unique energy gap, it exactly matches frequencies that belong to your visible spectrum. So when जब यहाँ से electron jump करता है ना, there's an electron in the lower energy subshell, right? And it jumps to a higher energy D subshell. And all of a sudden it absorbs a frequency from the blue spectrum. Then you'll notice something. You'll notice that the blue light is missing. ठीक है, तो ये idea clear है कि why are transition metals colored, and ये भी idea clear है कि there's nothing special about them being colored. Almost all atoms actually do that. Is that clear? Yes
सर.
हाँ जी.
सर अगर इलेक्ट्रॉन्स मिस में लाइक ये जो ब्लू कलर सबशेल्स हैं सर, तो लाइक आपने कहा कि वो रिकॉग्नाइज हो जाएंगे?
क्या हो जाएंगे?
लाइक वो जब इलेक्ट्रॉन्स मिसिंग होंगे ना ब्लू सबशेल,
इलेक्ट्रॉन्स मिसिंग नहीं हो रहे, फ्रीक्वेंसी एब्जॉर्ब कर रहा है वो.
यस.
अगर वो ब्लू फ्रीक्वेंसी एब्जॉर्ब कर लेता है तो ब्लू फ्रीक्वेंसी आपको नहीं नजर आएगी ना, क्योंकि वो तो इलेक्ट्रॉन लेके चला गया, इलेक्ट्रॉन ने एब्जॉर्ब कर लिया. बस समझिए बात, तो तुम्हें ब्लू फ्रीक्वेंसी तो नहीं नजर आएगी.
ओके सर.
अब ये आइडिया इज कि इफ एन इलेक्ट्रॉन, मतलब ये आइडिया क्लियर है कि there's an energy gap that is created between the D subshell when it forms a complex, right? The whole idea is that imagine अच्छा वो मैं आइडिया देता हूँ कि reflection basically. So imagine there's this complex and all sorts of frequencies are actually falling onto this complex. Well, all of them. So let's say there is radio waves that are coming in, and then there's blue light or frequencies that belong to blue light. Then there is red frequencies. Then maybe there's ultraviolet light, which you can't see. So all these frequencies are falling, and you're standing over here. Okay, so you're standing over here. Now, one of the electrons in the D subshell, it decides to absorb and move into an excited state. Okay, it needs a certain amount of energy for that. And that particular energy gap matches frequencies that belong to the blue spectrum. So ये blue light आई है इसके ऊपर and it falls onto this complex and the blue light gets absorbed, right? And who absorbs it? The electron absorbs it. The electron decides to go absorb that frequency and jumps to the higher energy because that frequency exactly matches your energy gap. So now all the other light, I mean, all the frequencies that are falling, they're going to get reflected, right? ठीक है हमेशा याद रखना कि आप क्या देखते हो you always see what is being reflected. Like if you see a wall, it's basically the light that is falling on the wall and it's getting reflected from it and you're seeing that light. So what you'll see is you will obviously not see the ultraviolet light, but you'll obviously be receiving it. So now you'll also see the red light. You won't see the radio waves coming back at you because you obviously can't see them. Your eyes cannot see them, right? So what color will you see? You'll see red color. Is that idea clear? Abhi, is this clear?
Yes, sir.
So isko kehte you always see a complementary color. Okay, the next time if you see something that's red, the thing is the only reason you see it as red is because it had nothing to do with being red. Because red ko kuch kar nahi raha tha. It was, I mean, the red light came and got reflected back and you were able to see the red light. It was actually absorbing the other color. It was absorbing the blue color. Okay, that's why you can't see the blue color because it's absorbing all the blue frequencies. So you always see what's left. I mean, you always see the rejected colors. ठीक है तो अगर आपके कपड़े येलो रंग के हैं तो उसका मतलब है your clothes have nothing to do with yellow. It's, I mean, your clothes are, I mean, they receive the yellow light and they just send it back to your eyes. They don't do anything with that. वो बाकी colors आपके clothes ने absorb कर लिए. ठीक है, so you always see a complementary color. तो बस इसको sum up कर लेते हैं quickly, ठीक है? हाँ, copper blue आपको इससे नजर आता है copper compounds. You see like copper with water complex. It's the reason you see it as blue. Okay, यहाँ में मैंने उल्टा लिख दिया. I didn't see that. You would actually see the blue one. You won't actually see the red one actually. So blue आपको इससे नजर आता है because it's not doing anything to the blue. It's actually absorbing all the other colors from the spectrum, but it's not absorbing the blue color. तो आपको हमेशा उल्टा color नजर आता है. You see the complementary color. ठीक है, क्लियर है बात? तो बस मैं जल्दी से इसको क्विक रिकैप के transition metal complex have D subshells. The D subshells are identical, but they split into two different energy levels because of when they form a complex, because of the repulsion from lone pairs. Dehydrated copper sulfate will not have water. तो अगर वो dehydrated होगा ना तो उसका मतलब है कि the D subshell will be all, they will all be identical. So there won't be any energy gap between them. which is why anhydrous copper sulfate is actually white in color, क्योंकि उसमें ये delta E होता ही नहीं है. वो water आया था ना, water is the one that's actually splitting the D subshell. ठीक है? So you remove the water, it's going to turn back into white. It will stop absorbing any colored frequencies because there's not going to be any delta E. ठीक है, ये भी clear है? हाँ.
सर और बाकी ligands भी इस तरह से करें कि वो split करेंगे D subshells को.
हाँ, जब भी ligand आएगा ना, कोई भी ligand आएगा, तो जो D subshell है ना, because of repulsion, the D subshell will split into two sets of energy levels, and there's going to be a delta E created, and this delta E is exactly going to match frequencies that are part of the visible spectrum. तो ये delta E unique है, ठीक है? बाकी atoms में भी energy gaps होते हैं, like sodium के अंदर there's an energy gap, like electron jumps from the lower energy to a high energy, right? वो जो Lyman series और Balmer series और वो सारे हैं ना, Passion series, ठीक है? लेकिन all those energy gaps are either much bigger or much smaller. So they either, if it's bigger, then they might absorb gamma rays or X-rays. So, or if they are smaller, then they might absorb frequencies that belong to radio waves, right? तो वो आपको नजर ही नहीं आती. तो वो अगर वो absorb भी कर ले तो आपको कोई फर्क नहीं पड़ेगा, ठीक है? जैसा आपका फोन जो है ना, it emits radio waves, आपको तो कुछ नहीं नजर आ रहा ना. हाँ, अगर वो होता ना कि if you were able to see radio waves, तो आपका फोन टॉर्च की तरह काम कर रहा होता, लाइट उसमें से emit हो रही होती, but you're not able to see radio waves. Your sensors in your eyes, they can't actually see radio waves. चलो ठीक है, इसका फिर नेक्स्ट टाइम हम लिखते हैं. हाँ जी. नहीं, you won't Alicia, you won't get any questions regarding anything numerical about this. It's just going to be a general question. I'll write the answer for that. There's going to be 2 typical questions, and we're going to write the answer in the next class then. ठीक है?
सर
हाँ.
सर जो 5 सीरीज आपने मेंशन की, सर अब ये हमारे सिलेबस में है?
नहीं, A levels में तो नहीं है, उसमें FSC में होती है या एंट्रेंस टेस्ट वगैरह में, वो इसमें नहीं है. तो ठीक है, इसकी एक्सप्लेनेशन और इसके ऊपर जो क्वेश्चन आएगा, क्वेश्चन नो न्यूमेरिकल क्वेश्चन, जस्ट अ सिंपल एक्सप्लेनेशन ऑफ व्हाई आर दे कलर्ड. फर्स्ट क्वेश्चन. सेकंड क्वेश्चन इज व्हाई डू दे हैव डिफरेंट कलर्स. लाइगेंड चेंज करोगे तो कलर क्यों डिफरेंट हो जाता है? क्योंकि एनर्जी गैप चेंज हो जाता है. If you have a different ligand, that will create a different amount of repulsion. So that will result in a different energy gap. If you have a different energy gap, a different frequency will be absorbed, which is why different ligands will have different colors. Water की जगह अमोनिया डाल देते तो it becomes dark blue. OH आ जाता है तो it becomes light blue. ठीक है? So the energy gap starts changing. चलिए ठीक है, ये फिर next class में ना we'll just write the answers to this. नहीं, और कह रहे कि पहले ये तो खत्म हो जाए, नेक्स्ट वीक ये खत्म हो जाएगा. वी स्टिल हैव some stuff left in this. ठीक है? चलिए, ओके एवरीवन. ठीक है, अल्लाह हाफिज.